All right. Thank you for tuning in today. I'm Jeremy Deeds, an aquatic ecologist with the Maine Department of Environmental Protection in the Lakes Assessment section. Today, I'm going to talk about some work we're doing with some long-term trend data sets and how climate change is shaping how we are thinking about doing our lake assessments in the future. As many of you know, we do a lot of trend analyses in our lake assessments at DEP. For when we're looking at lake condition. We are interested in how lakes are doing over time, if the condition is changing over time. And we are able to do a lot of this because of the extraordinary work of hundreds of professional and citizen scientists collecting lake monitoring data every year. So what we're looking at here is a time series plot of disk transparency in meters from 1990 to 2018. So the blue dots are the annual median Secchi transparency values for this lake. And then the black line is a low S moving average line. So looking at this trend plot here, we can see it goes up and down over time, but largely it's pretty stable. We run into issues, though, if we look at only a portion of the trend at a time. So if we look at only the first 15 years, it looks like we have a declining Secchi disk transparency. If we look at the following 10 years, it looks like we have an increasing Secchi disk transparency. Now, it's not as much of an issue when we are looking at the entire time series, 1990 to 2018, because we see how it's going up and down. But if we only have a portion of the time series, say we only have the previous 10 years of data in the blue, or we're doing an assessment in 2005, which makes it look like it's been decreasing in the previous 15 years. Then we have an incomplete set of information to base our assessment on. Now we know that there are natural fluctuations. We can see it in this trend series here. But why is that happening? Is it due to weather patterns? We know that things like precipitation and air temperature can influence lake clarity on a year-to-year basis. But importantly, is there anything going on in the watershed that would influence lake clarity? So teasing out these natural fluctuations and background fluctuations happening in lakes from things that are going on locally, they're very important for our lake assessments and something that we need to be able to address when we're looking at a lake's condition. To get a better idea of where these natural fluctuations are coming from and understand why they're happening, we're using the Maine lake classification. So this was detailed in a report that came out last year. And it essentially groups lakes into three separate geographic regions of Maine: coastal, inland, and northern, and then stratifies lakes in each region by maximum depth. So we have deep and shallow lakes in each of the three regions. The depth classes are delineated by maximum depth of 10 meters, which is the average photic zone for Maine lakes. So what we can do with each of these lake types is look at the lakes that are in the most undisturbed watersheds for their lake type. Those lakes, which have minimal human activity in the watersheds, we can make the assumption that changes in those lakes are due to regional factors, not local factors. So we can base our trend series on those reference lakes to get an idea of what those natural fluctuations are. So here on the right, you see a series of 5 time series plots for each lake type. Notice that the bottom one, Northern Lakes, has deep and shallow lakes grouped because there is not enough data on reference lakes in the northern region to have both deep and shallow lakes. So you can see that there are not only differences in water clarity measured in meters among types, but there's also difference in the patterns and how those clarity changes are happening over time. So now that we have these different time series of reference lakes across Maine for the different lake types, we want to see if we can figure out what's driving these differences and fluctuations among the different types. To do this, we're going to use something called dynamic factor analysis. DFA is a multivariate analysis that compares and evaluates many time series to each other. It allows us to explore differences and similarities among lake types, and it also lets us measure the importance of weather patterns on natural fluctuations and water clarity. so we can attempt to develop more metrics to understand why we're seeing the differences that we are. Perhaps most importantly, why do we care about this? We care about this because DFA will hopefully help us organize and interpret all this information we're seeing from these large time series data sets. And if we can increase our understanding of the processes that are shaping these changes in water clarity over time, we'll have more informed assessments. We'll just have more information to make better assessments and better decisions about lakes if we can understand the process better. So I'm not going to go into great detail about DFA and the methods involved here today, but I wanted to give a basic overview of the process and the analysis so that we can have a discussion on what we're seeing. So the first thing we do, we take those Secchi transparency measurements. Remember, those are means based on the number of reference lakes in each lake type. So we're going to take those measurements and convert them to z-scores, because we're not as interested in the absolute differences in lake clarity among lake types. We're interested in how each lake type is changing from year to year. So by taking the z-scores, we're now looking at the standard deviations around the mean. So the z-score converts the mean of each lake time series to 0, and the differences are measured by the standard deviations. So now you can see that each time series has a similar shape and pattern, but the mean is 0 for each of them. So one of the main components of the DFA is producing these what are called common trends. Now these common trends illustrate similarities that exist among the different time series. So here we have 5 lake types that are distilled into 2 separate common trends identified in this DFA. So common trend 1, which shows an oscillation that goes from moderate high to low to high, and then common trend 2, which shows more of a steady increase along the entire time series. Next is to associate the different lake types with each common trend. Loading factors. So this loading factors are just a measurement of the strength of association with each lake type. So what we're seeing in trend 1 is that the lake types in the coastal region, coastal deep and coastal shallow lakes, and then the northern lakes are more strongly associated with common trend 1 than 2. And the inland lakes, both deep and shallow, are more strongly associated with common trend 2. So already now we're seeing some disparity in groupings on how these lakes are changing over time based on these lake types and the regions that they are in. So now we can look at this DFA model, okay? So it's a linear model. And what we're looking at here, the black dots are still the same Secchi transparency data, the z-scores for year to year for each lake type. But now we have these black lines, which are the DFA model fits. Those model fits are based on the type of variance in the DFA model, the common trends, and the loading factors that associate those common trends with each lake type to different degrees. So now what we want to do, we want to add a covariate to see if model fits can be improved, and we can explain a little bit more of the variation that we see among these lake types. So these covariates, we're looking at weather variables. So we use statewide averages obtained from the University of Maine Climate Change Institute. And we focused on precipitation and monthly totals, and air temperatures and monthly averages. So using those monthly values for precipitation and average temperature, we then aggregated those values into many different time periods to have a variety of metrics based on those 2 weather variables. So we aggregated them into seasons, the 4 seasons of the year, a stratification period for Maine lakes, which we used April through September, and then water year, which is the year that begins in the previous year's October and goes through the September of the current year. Okay, so now what we can do, we're going to have another look at our model fits, but we're going to add in the covariate from the weather variables. So what we found is that precipitation during the stratification period, so that's total precipitation from April to September, gave us the biggest increase in model fit. So it was the strongest associate with the different um, for the different lake types. The biggest difference you can see in these model fit lines is how much more wiggly the covariate model fit lines are, because for every year they're incorporating the precipitation data, and you can see it looks like the model fit lines are more responsive to the differences in water clarity that we're seeing year to year. Now what we can do is look and see how the model fit works for each individual lake type instead of all lake types as a whole, which is what this particular part is doing. So to check the model fit for each lake type, we can use the sum of squares ratio, which is the ratio of the sum of squares of the residuals divided by the sum of squares of the observations. Now the residuals are the differences between the data and the modeled estimates, and the sum of squares of the observations is the sum of squares between each observation and the overall mean. So here, the lower number equals the better fit. So you can see the highest sum of squares ratios for the models with no covariates is the northern lakes with 4.22, which makes it the poorest model fit. Coastal deep lakes have more of a moderate value, 1.11, and then coastal shallow and inland deep and shallow lakes all have sum of squares ratios less than 1, with inland deep having the lowest value and therefore the best overall model fit. So now what we can do is take a look at the sum of squares ratios from the covariate model, which incorporates precipitation. What we can see is that almost all, except for one lake type, went down, which means the model fit improved. The delta SS ratio is the difference between the two SS ratios. So a larger delta SS ratio means a bigger improvement in model fit. So here, the model fit for the northern lakes went from 4.22 to 0.47. So the delta SS ratio is 3.75, which is the largest for all lake types. Coastal deep and shallow lakes and inland shallow lakes had more of a moderate increase, and inland deep lakes actually had a small decrease in model fit, but since the model was already so strong for this lake type and the delta SS ratio is so close to 0, we're thinking this was probably a negligible change in model fit. Just to help visualize what we're seeing here with the precipitation data, let's take a look at the time series for the precipitation values over the stratification period. So that plot is on the bottom. So again, we're looking at z-scores of the precipitation data. Now, from the water clarity time series you see on top, you'll notice that for every lake type, starting at about 2010, all lake types increase in clarity all the way through to 2018. And if you compare that to the precipitation data, the plot on the bottom, there is a low point in precipitation at 2010, but after that, there's an increase in steady decrease all the way to 2018. So that upward trend in water clarity since 2010 that affects all lakes coincides with that decrease in precipitation from year to year in the precipitation plot. So it seems like that's what's maybe driving the importance of the precipitation data and explaining the Secchi disk transparency time series. So let's try and unpack this and talk about what we learned from the DFA. So the first thing was the common trends. 2 separate common trends were identified among the 5 lake types. And those common trends identified differences and similarities among the lake regions, most of all. So common trend 1 showed shared patterns in water clarity for the coastal lakes, both deep and shallow, and northern lakes, which shows that oscillating water clarity pattern. Trend 2 was more strongly associated with lakes from the inland region, deep and shallow. This one shows more of a steady increase in water clarity throughout the entire time period we looked at here. So thinking about water clarity on a large scale across the state, the water clarity in Maine lakes was most strongly related to precipitation totals during the stratification season here in this analysis. So the mechanism here would be increased precipitation leads to increased erosion from the land and increased nutrient runoff into waterways and lakes. We did look at air temperature metrics as well, which did show improvement over the model with no covariates, but the effect was not as strong as the precipitation metrics here. So we're seeing that the precipitation covariate had the strongest effect on lake types, but it was different among lake types. So it looks as though some of our lake types may be more sensitive to precipitation than others. And sensitivity just meaning that they are influenced more by precipitation than others. So for inland shallow lakes, there was actually a decline in the model strength with the covariate, but since it was already a very strong model and the decline was slow, we're thinking it's likely just negligible, just a function of the mathematics more than anything. Coastal deep, coastal shallow, inland deep lakes all showed a moderate improvement in model fit. So they were, moderately, the model fit was moderately increased by using the precipitation data. And then the northern lakes had the largest improvement in model fit. So in general, what this really tells us, it underscores the role of precipitation and its effect on water clarity and lake condition. It's always nice when things sort of come together in a way that you expect them to, or it makes sense with what you think you already know. But it's always nice when you have data to support what you thought you already know. And it also gives us this metric of precipitation during the stratification period as a tool to help describe what's going on in our lakes year to year. And as you know, the more tools we have in our toolbox, the better our lake assessments can be. So looking ahead, annual precipitation is expected to increase. It's been increasing in Maine over the long term, and especially since 1960. It's been double the rate, and intense events are more common. And all this information is in the Maine's Climate Future report by Fernandez and others that came out in 2020. So as precipitation is expected to increase, the way we characterize baseline water clarity is also expected to change. If precipitation is increasing, we're expecting that lake clarity across the state will decrease along with it. So baseline water clarity has always been a moving target. We talked about the natural fluctuations back at the beginning here. But that baseline might be expected to decrease as we experience a future with greater precipitation. We may see that in terms of further fluctuations, greater fluctuations, and that we're expecting as the climate changes. Really, it just becomes even more important to track what's going on in our reference lakes over time, because it's our reference lakes that will let us know what's going on at a regional level, so that we can better tease out what's going on with lakes at local levels. So the take-home messages here: more precipitation leads to reduced lake clarity, but some of our lake types might be more sensitive to precipitation than others. Expected future increases in precipitation may lead to reduced baseline levels of water clarity across all Maine lakes. And it really underscores the importance of lakeshore and watershed resiliency against erosion, because that will only become more important in the future if we have greater amounts of precipitation that are causing more erosion into our waterways. So next steps, we want to continue examining the role of weather patterns in our different lake types. We'd like to explore how different water quality variables are responding to these patterns. So total phosphorus, chlorophyll A, things like that. We also want to look at things like stratification dynamics, mixing depths, and thermocline positioning, how those things are changing over time, and also the availability of cold water habitat. If thermocline positions are changing and water might be getting warmer, have less oxygen, we want to see if lakes are having changes in whole lot of habitat availability, which we can base off of temperature and dissolved oxygen profiles and lake bathymetry. So, like I keep saying, studies and results like these, we want to be able to use them to enhance our lake assessments. If we have a better understanding of our systems, we can have more informed lake assessments, which lead to better management decisions, and not just decisions at DEP, but for anyone that's working with Maine lakes and is making decisions about what's best for lakes. Hopefully these tools can help everyone in the state have more information. I'd like to thank my co-authors on this project, and also my predecessors at DEP and all the lake monitors out there that have been collecting quality data for so long. It's the longevity of the program that makes analyses like this possible. Things that started way before I was around, and people that had the foresight to develop these programs early on and had the ability to keep things going over the years, which allows us to look at data in this way, which is just hugely valuable. And that's all I have for right now. Thank you very much.